The simplest possible example of a Fourier transform of any function is a function that's got a constant value 1 in a certain interval and 0 everywhere else. So this is a classic example. It's known as a bump function. So you turn the bump on at -1 and you turn it off at +1. Now, a Fourier series, if you notice, has to be periodic from -infinity to +infinity. If it's not, you have to extend it either as an even or odd extension from -infinity to infinity. But that describes something that's highly artificial. It describes something that goes on forever. Now, there are some things in the universe that go on forever, like the rotation of a neutron star goes on for a long time. So in those cases, a Fourier series might be used. But a Fourier transform is used when there's a one-time event, like an impulse tap. You tap something like that, and you want to find what happens from -infinity to +infinity. Those kind of impulse taps and sudden impulsive percussive things are ideal for Fourier transform. By the way, optics is all over this Fourier transform concept. So the example that we're going to be doing is also the intensity pattern of light when it goes through a slit of length or width 2. No units, unfortunately. So if you want to put units into everything, you might have to work a little bit more. Along the way, I'll teach you how to evaluate the famous integral known as the Fresnel integral, which is the integral from 0 to infinity sine beta over beta d beta. This integral I evaluated using the techniques of differentiating under the integral sign by considering the auxiliary integral e to the minus some alpha or beta x sine beta d beta, and then differentiating with respect to x to get rid of this beta, and then playing all kinds of tricks. Well, this gives us an alternative way of doing this. In mathematics, the function sine beta over beta is called sinc beta. It's a very important function in diffraction theory, and the intensity pattern is proportional to sinc squared. So this is the amplitude of the single slit diffraction pattern. We have to find the Fourier transform of the bump function. The bump function is this. Well, if you want to put a mathematical definition of the bump function, let's do that. It's f of x equals 1 if x is between -1 and 1, and it's 0 elsewhere. That's the mathematical definition of the bump function. Now all we need to really do is evaluate the various integrals involved in Fourier transforms. Remember the basic definition. You're replacing the summation sign with an integral sign. So that's -infinity to infinity. That would be your n variable. Instead of c sub n, you write g of alpha. And instead of e to the I nx, you write e to the I alpha x. And instead of summation sign over n, you write integral over alpha. It's as simple as that. Where g of alpha is 1 over 2 pi, the old mathematics normalization is what we're going to stick with in this course. Infinity to infinity, f of x e to the minus I alpha x dx. So that's the analog of getting your coefficients Cn, and this is called the Fourier transform, the integral transform of f. Let us find what g of alpha is, because g of alpha will help us find what f of x is. F of x requires us to find g of alpha first. So g of alpha is the first integral that we need to find. Let's work on that. G of alpha is 1 over 2 pi. This function is really easy because it's just got the value 1 when it's not 0. And it's only not 0 from -1 to 1. So the integral simply reduces to -1 to 1. 1 times e to the minus I alpha x dx. That's an integral that can be evaluated very easily. It's 1 over 2 pi. The integral of e to the alpha x dx is 1 over alpha. So integral of e to the minus I alpha x is 1 over minus I alpha. And then I get the exponential back. Now one thing I can do is I can take the minus sign outside and take the 2 along with the alpha. So let me do that. 2i. I'll take the 2i along with the alpha. Let me first do this numerator. So let me hold off on that. 2 pi I alpha times the numerator gives me e to the negative I alpha minus e to the positive I alpha. So one thing I can do immediately is take the negative sign inside. So I get e to the I alpha minus e to the minus I alpha. But that looks an awful lot like what sign would be if only there was a 2i helping it along. And so what I'll do is I'll take the 2i down there, leaving me with just 1 over pi alpha outside. So this is just sine alpha over pi alpha. Or if you want to use the newly minted Sinc function, it's Sinc alpha over pi. Therefore, we can expand our function f of x in a infinite series as follows. It is Sinc alpha over pi e to the I alpha x d alpha. Finished. We have finished this problem. But our aim is to still integrate that integral, which I'll call I, which is the Sinc or the Fresnel integral. Fresnel is was one of the great contributors in the original theory of optics. Fresnel, and the other name is Fraunhofer. So there's even a famous lens called Fresnel lens based on Fresnel's work in diffraction. Let's go on to calculating this. Now the way you play this game, by the way, whatever theorems we had for the discrete case is also there for the continuous case. So our good old friend Dirichlet is here also. Dirichlet's theorem says that the Fourier series converges at jump discontinuities to the midpoint value. The midpoint value is, of course, half. So at 1, this is going to be 1/2. Let's put the value 1 in that equation. So I'm going to get the integral minus infinity to infinity Sinc alpha over pi e to the I alpha d alpha. Now to evaluate this, I can take the pi outside. Let me now restore what Sinc means. It's sine alpha over alpha. E to the I alpha can be expanded by our good old friend, the Euler's formula. So that's cosine alpha plus I sine alpha d alpha. Now, cosine alpha times sine alpha. Cosine is an even function, sine is an odd function, but alpha is an odd function too. So sine alpha by alpha is actually an even function. That's an even function, and that's an odd function. The product of even times even is even. The product of even times odd is odd. Therefore, this will not contribute, and so we have just this. That as will be the case, otherwise you're going to get half, which is a real number, equal to something plus an imaginary number that will not look good at all from the complex analysis point of view. So it's a good thing that it went away. Now, if it didn't go away, we would conclude that that other integral would be 0, because that's the only way you can make a real part equal to an imaginary part. So that would be the inevitable conclusion that you get. Suppose this was even and that was even too, it would mean that the second integral is 0 because it multiplies I. But that's not the case here. The case is simpler than that. So I'll get 1/2 equal to the integral of minus infinity to infinity Actually, I'm going to take the pi over to the other side. So I get pi over 2 is equal to sine alpha cosine alpha over alpha d alpha. Sine alpha cosine alpha is sine 2 alpha. So I'm going to write this as 1/2 sine 2 alpha. And also, this integral, because this is an even function, can be doubled. So I can write 2 times integral from 0 to infinity, so that 2 will cancel with that, alpha d alpha. Now what I'm going to do is a change of variables, but rather than muck around with a change of variables, I'll simply do the following. I'll write sine 2 alpha d 2 alpha. Nothing sinful, because all I've done is multiplied and divide by 2. Now I can call 2 alpha beta. Alright, so alright, I have the change of variables if you like. So pi over 2 is going to be the integral from 0 to infinity sine beta over beta d beta, which is the integral from 0 to infinity sinc beta d beta. So we have found our important result, that the integral from 0 to infinity of sinc beta d beta is pi over 2. Just to give you a little understanding of what the sinc function looks like, it's actually very complicated looking. It's sine x divided by x. Alright, so basically as x increases, this thing is going to keep decreasing. But because at x equals 0, sine x over x, the limit as x equals 0, you spend half your calculus class, first calculus class, evaluating this limit in 10 different ways. It's equal to 1. The only way I remember anymore is L'Hopital's rule. So cosine x over 1 is what you'll get, which is equal to 1 at x equals 0. Because it's got a head start, it's going to have more area in the positive side than the negative side, because of this initial head start it's got. Okay, so this area down here, all the negative areas I'll color in bluish. Would not be as much as all the positive areas. The positive areas will easily dominate the negative areas, and that's why you're getting pi by 2. Now it's because it's an even function. If you find the other side, it's going to be another pi by 2. So if you did from minus infinity to plus infinity, the answer would be pi.